All right.
Go ahead and get started. All right. I'll start with synthetic division. This is a shortcut for dividing a polynomial by another polynomial. It only works when the polynomial in the denominator is a binomial, so it has two terms, and the first term is just x. So it can't have a coefficient in front, it can't have an exponent. So it's just x plus or minus a constant. So in that case, what we're going to do, so this method, maybe some of you are familiar with it, maybe you're not, but it looks a little strange at first, but I think you'll find that it definitely gets easier and saves time once you get the hang of it. So what I'm going to do is I'm going to take this number right here, and I'm going to take the opposite of that number and put it in like, so the opposite of 2 would be -2. I'll put it in that little half box right there. And then the next thing we're going to do is we're going to take the coefficients from the polynomial in the numerator, and we're going to put those all across here. Try to find that orange pen. Find that orange pen. Here it is. Okay. All right, so there's an invisible 1 there, so it'll be 1, 7, 13, 6. Then we're going to skip a space, draw a line like this. Then we're going to bring the first coefficient down. That's 1. And then we're just going to multiply this times the number in the box. So 1 times -2 is -2, and it goes right there under the 7. I need to zoom out a little bit, don't I? All right, and then you're basically adding, but since it's negative, it's like you're subtracting. So 7 minus 2 is 5. And then 5 times -2 would be -10, goes right under the 13. 13 minus 10 is 3. 3 times -2 is -6. And then 6 minus 6 is 0. All right, and you might want to rewind it and like go back over, just make sure you followed it if you need to. All right, so that's the remainder. That last number right there is the remainder. So in this case, the remainder is 0, so that's good. All right, and then we're just going to fill in the x's. All right, so we divided x cubed by x. So the answer is going to start with x squared. So it's just going to be 1 less than whatever this is. It's going to be x squared plus 5x plus 3. All right, so your final answer is x squared plus 5x plus 3. All right, and there was no remainder in that case. All right, so number 2, same thing. So the opposite of this is going to be -2 again. So -2 goes in the box. And then there's an invisible 1 there. Now you have x to the 6th, and then it skips over x to the 5th. So you have to insert a 0 in place for x to the 5th. And then -3, 2, -6, -5, 3. So draw a line right here, bring down the 1. So 1 times -2 is -2, 0 minus 2 is -2. -2 times -2 is +4. -3 plus 4 is 1. 1 times -2 is -2. 2 minus 2 is 0. 0 times -2 is 0. -6 plus 0 is -6. -6 times -2 is +12. -5 plus 12 is 7. 7 times -2 is -14. And 3 minus 14 is negative 11. Okie dokie. Let's see. Oh, no, that's good. Okay. So now we have a remainder of negative 11. So this is going to be x to the 5th minus 2x to the 4th plus 1x cubed plus 0x squared minus 6x plus 7. And then the remainder goes over the original divisor, which is x plus 2. All right, so I'm just going to rewrite that a little bit neater. My final answer is going to be x to the 5th minus 2x to the 4th plus x cubed minus 6x plus 7 minus 11 over x plus 2. There's my final answer. Number 3. All right, so I'm going to do the opposite of this number goes in the box. So in this case, opposite of negative 1 is positive 1 in the box. And then I've got a 1 for x to the 4th. All right, and then I don't have any x cubed, x squared, x, so that's going to be 3 zeros there, and then negative 1 at the end. One, 0. All right. And this is for the answer. It's going to be x cubed plus x squared plus x plus 1. That's my final answer. X cubed plus x squared plus x plus 1. That's our final answer for that one. All right, so then number 4, it was basically wanting us to do the same thing, just with a little bit different form. So they've already changed the sign, basically, is what they did right here. So the number that goes in the box is going to be negative 4. And then our coefficients are going to be 2, 3, negative 16, and 10. Two, negative 8, negative 5, 20, 4, negative 16, negative 6. All right, so now they're asking us to write the answer in the form of f of x. So f of x, which is equal to the original function, is equal to x minus k. So in this case, k was negative 4. So x minus negative 4 is actually the same thing as x plus 4 times q of x. So that's the quotient, which is going to be 2x squared minus 5x plus 4. All right, plus the remainder. So in this case, the remainder is negative 6. So plus negative 6 is also the same thing as minus 6. All right, and that's what they're looking for that answer. All right, so this is actually equal to the original function. It's just kind of factored out, but not really because it has a remainder. So. And then number 5, same thing. So put that 2 in the box. Then your coefficients, you have negative 1, 1, 3, negative 2. Then we're going to do our synthetic division. Negative 1, negative 2, negative 1, -2, +1, +2, and 0. So this time our remainder is 0. So to write our answer, it's going to be f of x equals x minus k, and in this case, k was 2, times the quotient. That's going to be x squared. So it's going to, the quotient is going to be -x squared minus x plus 1. And then there's no remainder. So if this was a question on the homework, I'm not really sure if they would want you to put +0, but I wouldn't think so. So this is actually a factored form of the function. All right. And then the remainder theorem. So basically it's saying that if you divide that, whatever your remainder is equal to the function value. So I'm going to put 4 in the box and I'm going to do my synthetic division. That's going to be -1, 8, and then it skips over the x term, so there's going to be a 0, and then 63. All right, so whatever I get for my remainder is going to be equal to f of 4. So -1, -4, +4, 16, 16, 64, 127. Okay, so in this case, they're not asking for the quotient, they're basically just asking for the remainder. So f of 4 is equal to 127. That's kind of just a shortcut. All right, so if f of k equals 0, then k is said to be a 0 of f of x. So is 1 a 0 of this f of x? So to determine that, we'll just do our synthetic division, putting 1 in the box, and we just want to see if our remainder is going to be 0 or not. So if our remainder is 0, then the answer will be yes, and if the remainder is not 0, the answer will be no. 2, 2, 11, 11, -5, -5, and 7. So due to the fact that 7 is not equal to 0, the answer is no. 1 is not a 0 of that function. All right. All right, so basically using that same tactic, we can determine if something is a factor. So to check if x minus k is a factor of p of x, divide p of x by x minus k. If the remainder is 0, it's a factor, otherwise it's not. All right, so we want to know, is x plus 1 a factor? All right, so we're going to put -1 in the box. And then we're going to have 2. And then it skips over x squared, so that's going to be 0. And then 1, and then 2. So 2, -2, -2, 2, 3, -3, -1. So since -1 is not equal to 0, therefore the answer is no, x plus 1 is not a factor of that. All right. And then let's see, factor f of x given that k is a 0 of f of x. Okay, so k is 2, so we're going to put 2 in the box. And then we have 2, -3, -5, 6. And then we have 2 times 2 is 4. And so that's going to be 1, 2, -3, -6, and 0. So they already told me that 2 was a 0, so that makes sense that I came out with a remainder of 0. All right, so that's 2x squared plus 1x minus 3. Okay, so now I'm trying to factor it. So f of x, which is the same f of x I have up here, now I know that is equal to x minus 2 times this quotient, 2x squared plus x minus 3. Okay, so that's partially factored, but I might be able to factor this as well. So let's see if I can. I'll bring this part down. Let's see. So you could use the AC method, or you could guess and check. So it's got to be, I'm going to try guess and check. And I think that would be it. Let's see. That would be 2x squared. That would give you the -3. And then for the middle term, that would give me 3x minus 2x, which gives me the positive 1x. So yep, that is the correct factorization. So now that is the fully factored form of the function. All right, and then number 3 is the same thing. So in the box goes -5. And then we have 8, 50, 47, -15. And then 8, -40, 10, -50, -3, +15, and 0. So now we know that f of x equals x minus -5. So that's the same thing as x plus 5 times 8x squared plus 10x minus 3. All right, so we can factor that. So that would be 8x squared, that would be -3. And then that would be plus 12 minus 2, which would give me the positive 10x. So yep, that's it. All right, so you could use the AC method or you can guess and check. And I have a video about that. I believe it's lesson 6, which is all about factoring. Yeah, lesson 6 from June 25th. So if you want to review factoring, go to that video. Okay. All right. Given that 1/2 is a 0, find all other zeros. Okay. So that means I'm going to put 1/2 in the box. And then I have 4, 6, -2, -1. 4, 2, 8, 4, 2, 1, 0. So now I know that f of x equals x minus 1/2 times 4x squared plus 8x plus 2. Then let's see if we can factor that part. First of all, I know I can factor out a 2 from there. Once I do that, it'll be 2x squared plus 4x plus 1. And then if I was to factor that, it would have to be 2x plus 1 times x plus 1. That's the only possible thing it could be to make 2x here and then a positive 1 and all that. Let's check that. So 2x squared is 1. All right, so the outside, that would be 2x plus 3x, or I'm sorry, 2x plus 1x would equal 3x, not 4, which tells me that this doesn't work. So if that doesn't work, then I would need to use like the quadratic formula. Okay, so take this right here and use the quadratic formula on it. So 4x squared plus 8x plus 2 equals 0. So I can go ahead and just divide everything by 2, which would make it 2x squared plus 4x plus 1 equals 0. Then I can put it into the quadratic formula, which is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And I went over that just briefly in the last lesson, which was lesson number 7. So x equals negative 4 plus or minus the square root of 4 squared minus 4 times 2 times 1 all over 2 times 2. So that'll be negative 4 plus or minus the square root of, let's see, that'll be 8 all over 4. And then the square root of 8 can be broken down using a factor tree. So if we did a factor tree of 8, 2 and 4, 2 and 2, and then you have a pair of 2s. So you're gonna have a 2 on the outside and then that 2 on the inside. So that equals negative 4 plus or minus 2 square roots of 2 all over 4. And for simplifying square roots, I went over that in more detail in, let's see which lesson, the lesson about radicals. That was lesson 5, where I went over that in more detail if you wanted to review that. All right, and then finally we can reduce. So 2 goes into each of those. So x equals 2 plus or minus the square root of 2 all over 2. So those are my other zeros. Okay, so those would be known as irrational. So in other words, they're not rational because you have a square root left in your answer that can't be simplified. So those are non-rational zeros, but they are real numbers that could be plotted on a graph theoretically. Okay. All right, next up is the possible rational zeros theorem. All right, so this is just a way of figuring out all of the possible rational zeros for a polynomial. All right, so first of all, it's going to be any factor of c, which is c is the constant term on the end of the polynomial, so the one that doesn't have any x or any variable with it. And then a is the leading coefficient. So any factor of c over any factor of a. All right, so in this case here, c is negative 8, and then a would be 1, invisible 1 right there. So when a is 1, that makes it a lot easier because the only factor of 1 is 1. So your possible rational zeros for this are basically just going to be plus or minus any factor of 8. So any number that goes into 8. So that'll be plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Okay, and normally we would divide those by the factors of a, but that would just be dividing it by 1, which wouldn't do anything in this case. All right, now then in order to find the actual zeros of that polynomial, we're just going to test them out using synthetic division. And I always like to start with 1. Okay, and we'll know if it's a 0 if we get a remainder of 0. And if not, then I would move on to -1. And if that doesn't work, I'll move on to 2, and then -2, and then 4, and then -4, and then 8, and then -8, and so on. Okay, but we can probably, once we find one that does work, meaning it does give us a remainder of 0, then we don't have to test them all out. All right, so 1 in the box, and then 1, 5, 2, -8, 1, 1, 6, 6, 8, 8, 0. Hey, we got it on our first try. Yay! Okay, so now we know that 1 is a 0. All right, so now I would proceed to factoring the polynomial. So f of x equals x minus 1, because 1 is a 0, we know that. And then we're left with, so this would be x squared plus 6x plus 8. All right, and then that part should be pretty easy to factor, I think. So f of x, bring down the x minus 1. And then that's just going to be x plus 2 times x plus 4, because 2 times 4 is 8, and 2 plus 4 is 6. All right, so now we're done with the factoring part. That is the fully factored form of the function. And I'll finish answering part B, which was to list all of the actual rational zeros. So we have 1 is one of them. And then from looking at here, so it's the opposite of these numbers. So it's +1, -2, -4. Okay, those are all the rational zeros of the function. And in this case, they are all zeros of the function. All right. Multiplicities of zeros. Okay. All right, so multiplicities of the zeros. So once you have your polynomial in factored form, you can identify the multiplicities. So here's your A is a 0 with a multiplicity of n. B is a 0 with a multiplicity of m. So the exponent there is the multiplicity. So a lot of times maybe it's just 1, and that's fine. Okay, so right here we have a multiplicity, or I'm sorry, we have a 0 of -1 with a multiplicity of 2. Then we have a 0 of 1 with a multiplicity of 3. And then here, we would need to set this equal to 0 and solve for x. So x squared plus 10 equals 0. Subtract 10 from both sides. So x squared equals -10. Take the square root of both sides. So x equals I times, or plus or minus I times the square root of 10. Okay, so that's imaginary. The multiplicity on whatever that is going to be 1, but So we have I times the square root of 10 with a multiplicity of 1, and negative I times the square root of 10 with a multiplicity of 1. Okay, so technically those are zeros of the polynomial, but we're probably not going to do a whole lot with those because they're imaginary. So they can't go on a graph. So normally the zeros of a polynomial, the real zeros anyway, are the same thing as the x-intercepts of the graph. But if they're imaginary, then you can't graph those. Okay. Number 7. So I have a 0 of positive 5 with a multiplicity of 1. And then I have a 0 of negative 3 with a multiplicity of 1. And then I have a 0 of positive 1 with a multiplicity of 4. And then for number 8, let me set this equal to 0 and solve for x. So 7x minus 2 equals 0. Add 2 to both sides, so 7x equals 2. Divide both sides by 7, so x equals 2/7 with a multiplicity of 3. So I have a 0 of 2/7 with a multiplicity of 3. All right, and then x squared plus 9 equals 0. So subtract 9 from both sides, so x squared equals negative 9. And then take the square root of both sides. So that would be x is equal to plus or minus 3i. So positive 3i and negative 3i, and their multiplicity is going to be 2. And those are imaginary. So like this graph here, like for number 6, the graph would have 2 x-intercepts. For number 7, it would have 3 x-intercepts. And for this one, it only has 1 x-intercept because you don't count the imaginaries because you can't graph them. All right, we're finally going to start talking more about the graphs of polynomials. Let me zoom out a bit. Okay. All right, so here's an example of a polynomial. So just to review the terminology, let's say you have it in order with the term with the highest exponent is first. And so that exponent right there, that largest exponent is equal to the degree. Okay. And then whatever the number is in front of that, that's your leading coefficient. And that whole term is called the leading term. And then there's like your constant term on the end. Okay, so let's see. So in this example, the leading term would be 2.4x cubed. And that means that the leading coefficient would be 2.4 and the degree would be 3. And then for this example, they're not in order. So to put them in order, it would be x plus 12. So that's actually a linear function because it's just, x to the first power. But your leading term is just x. And it's got an invisible 1 in front of the x. So your leading coefficient is 1. And there's also an invisible exponent of 1, which means your degree is 1. All right. And the reason why we want to make sure we can identify all those pieces of information is because it's going to help us figure out the end behavior of the graph, meaning basically which way are the arrows pointing on the end of your graph when you draw it. Okay, and so here are some examples of polynomial graphs right here. All right, we'll look at more at those in a second. So whenever you have the degree is an even number, so meaning you have a degree of 2, 4, 6, 8, 10, 12, etc. If your degree is even, then that means that the arrows are pointing the same direction. So just like the parabolas of the graphs for like x squared, which we covered in the previous lesson, those arrows were always pointing the same direction, and that was a degree of 2. All right, and then so then that means if the degree is an odd number, so it means the degree is a 3, 5, 7, 9, something like that, then the arrows point opposite directions. Okay, so for example, the graph of x cubed looks sort of like this. Okay, and so that helps you remember the odd degree. So if the leading coefficient is, so for an even degree, if the leading coefficient is positive, the arrows both up. If the leading coefficient is negative, the arrows both go down. For an odd degree, then if the leading coefficient is positive, the arrows go like this, which is the same as your basic x cubed graph. And then otherwise they're flipped. Okay. All right. So let's see, hopefully you can read this. All right, so this right here, so that leading term is negative 4x to the 8th. Okay, so the leading coefficient is negative 4, and the degree is 8. So that means that, so the degree is even, so the arrows point the same way, and the leading coefficient is negative, which means they have to point down. So the arrows will be both pointing down. All right, so with these, so if we're matching it up to one of these, that would have to be graph B. And then this right here says negative 11x cubed, or in other words, negative
All right.
And then here, the leading coefficient is 5x to the 5th, or the leading term is 5x to the 5th. So leading coefficient is 5, degree is 5. So since the degree is odd, the arrows have to point opposite ways, and the leading coefficient is positive. So it's going to be like that. So if we match it up to a graph, it has to be C. And this one has, the leading term is 1/2 x to the 6th. The leading coefficient is 1/2, and the degree is 6. That's an even degree, which means the arrows point the same way. Positive leading coefficient, which means both arrows have to point up. So that matches with graph A. All right, let's see. And how many real zeros does each graph have? So real zeros are the same thing as x-intercepts. Okay, so real zeros are the same thing as x-intercepts. So graph A has 1, 2, 3 real zeros. And graph B has 1, 2, 3, 4 real zeros. And then graph C has 1 real zero. And graph D also has 1 real zero. All right. All right, and one more thing I have to say about this is that the maximum number of turning points is equal to the degree minus 1. Okay, so let's figure out what is the minimum degree just by looking at these graphs. So turning points is also known as like a relative maximum or a relative minimum. So like, for example, graph A has 1, 2, 3 turning points. So that means the minimum degree of that is 4. And then graph B has 1, 2, 3 turning points, which means the minimum degree is 4. And then graph C has 2 turning points, which means the minimum degree for that is going to be 3. And then graph D has no turning points. Okay, so based on that, you could say that the minimum degree might be 1. But if the degree is 1, then it would have to be a straight line, which it's not. And it can't be a degree of 2 because that would mean the arrows point the same way. So I'm going to say that the minimum degree then is going to be 3 for that as well. Okay. All right. And then next we're going to talk about why was it important to know the multiplicities of the zeros? Well, so the multiplicities of the zeros tells you what your graph looks like at that 0. So at that x-intercept. So if the multiplicity is 1, then when you zoom into that x-intercept, it basically looks sort of like a straight line. Just goes straight through it. If your multiplicity is even, then it kind of looks like a parabola at that point. It kind of like it bounces off, or you could say it just touches and then turns around and goes back the other direction. And then if it's an odd number higher than 1, so if it's like 3, 5, 7, something like that, then it looks similar to the x cubed function, which is like a squiggle. All right. And that's also going to be known as like an inflection point, which you'll learn about probably in calculus. Okay. All right. So for number 5, let's figure out the zeros. All right, now the one that people usually miss a lot is that this right here. So if you were to set x squared equal to 0, that would mean that x is equal to 0. So when you have something, regardless of what that exponent is, if you have an x in the front here that doesn't have like a plus or a minus a number, that's always going to give you a 0 at 0. And then the multiplicity is 2. So that's one that people miss a lot. Then we have a 0 at positive 5 with a multiplicity of 1. Then I have a 0 at negative 3 with a multiplicity of 1. Then I have a 0 at positive 1 with a multiplicity of 1. All right, here's another little trick that you need to know. The degree is equal to the sum of the multiplicities. All right, the degree is equal to the sum of the multiplicities, meaning if I add these together, that will equal my degree. So when your function is in factored form like this, the degree isn't as obvious as it is when it's in expanded form like this. Like here we can just obviously see that the degree is 3. But here it doesn't work that way. Some people think, oh, the degree is 2, but that's not right, okay? Because you have to add up. When it's in factored form, you have to think about, like, what if you were to multiply all this out to expand it? Well, what would your leading term be? Well, let's see, 2 plus 1 plus 1 plus 1, so equals 5. So if you add all those up, it equals 5. So your degree is 5. Okay. All right. So let me go ahead and put the zeros on. All right. there's that one, 0, and then 5. And then -3, and then 1. All right, so if the degree is 5, now the leading coefficient is +1. So that means the arrows go like that. All right, now I'm going to go ahead and draw my graph. Okay, so all of my multiplicities are 1 except for right here. So it's going to go straight through. And then when it gets here, it's going to bounce off. And then it's going to go straight through, straight through. So straight through, bounce, straight through, and straight through. All right. Now, with the information that we have right now, we don't have enough information to determine how high and low the peaks and valleys are. So the mins and the max points, we don't have enough info to determine those. So that's something that you will learn in calculus, but for right now, we don't have enough information or enough tools to figure that out. You can figure out the y-intercept by plugging in 0 for all the x's, which can sometimes help you. So sometimes you might see on the computer, they might ask you to graph the y-intercept to help you make the shape of the graph better. Here is the y-intercept right here, so that wouldn't actually help in this case. But. All right. All right, number 6. Okay, so this is an expanded form. So we're going to have to use the synthetic division to figure out the actual rational zeros. So see, the possible rational zeros are going to be ±1, ±3, ±5, and ±15. And then I'll figure out the actual rational zeros by using synthetic division. So putting 1 in the box, and then we have 1, 3, -13, -15. So 1, 1, 4, 4, -9, -9, -24. So because of the fact that -24 does not equal 0, therefore we know that 1 is not a 0. So next I'll try out -1 in the box. 1, 3, -13, -15. That'd be 1, -1, 2, -2, -15, +15, and 0. So now we know that -1 is a 0 of the function. So f of x equals x minus -1, which is really the same thing as x plus 1. All right, and then we have this right here is going to be x squared plus 2x minus 15. So if we were to factor that, it would be x minus 3 times x plus 5. So then we can see that we have a 0 at -1 with a multiplicity of 1. We have a 0 at 3 with a multiplicity of 1. And we have a 0 of -5 with a multiplicity of 1. So then we could go ahead and plot all of those. Okay. And the degree is 3, and the leading coefficient is positive, so the arrows go like that. And all of my multiplicities were 1, so I can just go straight through. Now, in this case, I actually know that my y-intercept is -15. So I don't have quite enough room, but I could just kind of pretend that I do. And I could say, oh, this is a negative 15 right here. We could just pretend that's true. No, it's really not. But that's okay. All right. And so that's what our graph would look like. So that's one of the things, like if you're doing this on the homework, they might have you plot that point and they'll give you enough room. Oh shoot, I was off the screen. Here we go. Here we go. All right. Okay. So there's that graph. All right, let's see here. So number 7. So in this case, the first thing I'd want to do is factor out my greatest common factor, which is x squared. And then that would be 3x squared plus 5x minus 2. All right, now this is just a quadratic, so I could probably just factor that. Okay, yeah, that works. All right, so I've got a 0 at 0 with a multiplicity of 2. And then if I do 3x minus 1 equals 0, add 1 to both sides, 3x equals 1, divide both sides by 3, so x equals 1/3. So there's a 0 at 1/3 with a multiplicity of 1. And then I have a 0 at -2 with a multiplicity of 1. All right, so my leading coefficient is positive and my degree is 4, which is even, which means arrows are both going to point up. Okay. This is going to be squished in there. Oh, well. All right, so that's a multiplicity of 1. That's a multiplicity of 2, which means it bounces off, and that's a multiplicity of 1. Both arrows are up. Okay. All right, so the graph would look sort of like that. Again, in this case, the y-intercept is 0. All right, number 8. So we're going to have to do possible rational zeros for this one. That'll be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16. Put 1 in the box. And then we got -1. It skips over x squared, so we got 0, 12, 16, -1, -1, -1, -1, 11, 11, 27, which is not equal to 0. So therefore that doesn't work. So then we'll put -1 in the box and then -1, 0, 12, 16, -1, 1, 1, -1, 11, -11, 5. That's also not equal to 0. So therefore that one doesn't work either. So next I'll move on to putting 2 in the box. -1, 0, 12, 16, -1, -2, -2, -4, 8, positive 16, 32, which is not equal to 0. So that one didn't work either. -2 in the box, -1, 0, 12, 16, -1, positive 2, 2, -4, 8, -16, and 0. Oh, all right, so finally we got one that worked. Okay, so we have f of x equals x minus negative 2, which is the same thing as x plus 2. And then we have negative x squared plus 2x plus 8. I'm not cool with having that negative in front of that x squared, so I would factor that out to the front. So then that would be x squared minus 2x minus 8. And then I should be able to factor that. That'll be x minus 4 times x plus 2. And then what you have here is you have x plus 2 and another x plus 2. So I'm going to write that as x plus 2 squared. Bring down x minus 4. So there is my fully factored form of the function right there. So now I can see that I have a 0 at negative 2 with a multiplicity of 2, and I have another 0 at positive 4 with a multiplicity of 1. And my leading coefficient is negative. My degree is 3, which is odd. So my arrow is going to look like that and that. So there's zeros. All right, now this is a multiplicity of, oops, that's not right. Or that. All right, so it's got to be up here and down here. Okay, so since that's a multiplicity of 2, it bounces off like that, and then that's a multiplicity of 1, so it goes straight through. Technically, my y-intercept should be 16. It's not really to scale properly, but let's just say that that's positive 16. Ta-da. Okay. I think that is good enough for this lesson. Thank you for watching. Let me know if you have any questions.